Okay, this is lesson 3.4 and part 3. We're gonna learn about linear motion. This is page 131 of your books. If you remember, linear motion, it's the motion on a straight line. It can be horizontal or vertical motion, but where s of t will be the position of the distance from the origin. That means that the velocity will be the rate of change of position with respect to time. This is going to be the velocity will be the change in the distance over or position over the change in time. Okay, how many kilometers this car advances in this particular amount of time, or how many steps have you moved in how many minutes, and the difference of minutes. Okay, let me rewrite this because it's supposed to be a T. Okay, so the sign of the velocity indicates if the object is moving, it's advancing forward or backward, if in case it's negative, or if it's going up or down in the case of vertical movement. And if you want to talk about the speed will be the absolute value of the velocity. Okay, it has no sign. Absolute value of the velocity, that's the speed. Okay, if you consider the graph that you have on the left, let's suppose that this is a car that it's moving, and it's a graph of distance versus the time. Okay, how many it advances. If you analyze the graph, you can see, if you think on the slope of the tangent line, remember that the slope of the tangent line is the velocity. Okay, so let's have or understand a few concepts about this. When the tangent lines are more steeper, that means that the car was speeding up. So if we want to know if it was speeding up or slowing down, in this case, for example, if you consider in the interval between 1 and 2, even if it's always increasing, that the slope of the tangent line is positive between 1 and 2, but it's more steeper in between 0 and 1. So that means that the car is speeding up in this first hour and then speeding down in the second hour. So in this case, this is speeding up and this is speeding down. Still advancing, still like positive slope, but like slowing down. Okay, standing still. When is the car not moving? When the car stop? Between the hours 2 and 3. This particular time, because why? How can we recognize that? Because we have a horizontal line, the slope is 0, so the car is not moving. Maybe this car stopped in a restaurant or in any place. Okay, what happened in that the graph goes up and then falls down in the interval between 3 and 4. So that means that maybe they go and come back into the place where it was, in that restaurant or wherever. Okay, so if you see in this part, it's speeding up and then going back. Okay, and then the average velocity, if you see the average velocity between 0,2, it's greater, the velocity between 3 and 5, the hours 3 and 5. So the average velocity is greater over the first 2 hours than the next part, because between 2 and 3, this part it was stopped, and here it's also speeding up, but it's that average rate of change was slower. I hope you understood this lesson. Let's go and let's talk again about linear motion, and we're gonna solve. Let me erase all this, and we're going to solve the next example, which is example number 5. In example number 5, we have a truck that enters to the off ramp of a highway at the time equals 0. Its position after t seconds is, this is gonna be example number 5. So time equals 0, it's when it's entering the ramp. And s of t, the position, the equation of the position equals 25t minus 0.3 t cubed meters for t less than or equal 5 and greater than 0. Okay, letter A, you have to find out how far is the truck going at the moment it enters, how fast, is it going. So the how fast, the velocity, the change of the position with respect to time. So we are going to find the velocity, which is the derivative of the position. How is the position changing in that particular time, which is the derivative in terms of t of 25t minus 0.3 t cubed, which equals 25 minus 0.9 t squared. Okay, and at when is that time when it was entering the ramp at t equals 0? So let's find the velocity at 0, which is also the derivative or the change in position at that particular time, which will be 25 meters per second. Remember that we were talking about meters. Okay, letter B, is the truck speeding up or slowing down? Okay, because b of t, the velocity, equals 25 minus 0.9 t squared, then if you see the graph of that equation, it's gonna be something like this. That means that this is the time and this is the position, the velocity, the velocity. So it's decreasing. So that means that it's the truck, it's slowing down. Okay, that was example number 5. Let's go and let's solve now example next example number 6. Before going there, we're going to talk about motion under the influence of gravity. Let me write down the equation. So if we're going to start studying motion with gravity, and if you remember Galileo's formula, the height or the position s of t, the velocity and the time of an object that it's tossed vertical in the air, it's given by these two formulas. This is the position and this is the velocity, which is the derivative of the position. Remember, so the position will be the initial position S0 or S initial plus initial velocity times the time minus 1/2 gravity times the time squared. And if we find the derivative of this one, then we will have the velocity. Okay, those constants of initial position is at time equals 0, and the initial velocity, it's a velocity at time equals 0 also. And we have the numbers, the values for the gravity, which is 9.8 meters per second square or 32 feet per second square. If you are thinking about an object tossed vertically, if it's something really easy like this, and you throw it into the air, it will go up and down. So if you think on that, and if you think on the slopes, of course it's going up, raising up, and then it has this slope, which is 0 at the top, and then it's going down. The slope is negative when it's going down. So if you understand this, you can realize easily that the point or the maximum height of this, it will be at this particular point when the slope is 0, because that's when it stops and then starts going down. So if you have, that's also that's the maximum height of that particular object that it's going up. So using all those concepts, we're going to solve example number 6 that says find the maximum height. So if we think again, that maximum height will be when the derivative equals 0. Okay, so let's do example number 6, and it says that a stone is shot with vertically upward with an initial velocity, so initial velocity that equals 50 meters per second. Okay, from an initial height, so S initial, that equals 10 meters. You have to find the velocity at t equals 2 and at t equals 7. So letter A, velocity at 2 and velocity at 7. Okay, and explain the change in sign. Okay, we have it, the velocity at equals 2 will be the derivative of position, which is the initial velocity, 50 minus gravity, which is 9.8 times the time, which is 2 the time. All this equals 3.4 meters per second. Per second. What I'm doing, I'm using this equation of the velocity, and I'm plugging in the value of the initial velocity and the value of the time in this case. Now I will compute B of 7, B of 7 will be 50 minus 9.8 times 7, which obviously will be negative. And the answer is negative 18.6 meters per second. And they ask us, what does this negative sign means? If you remember the graph that we saw, this is something like this. Then the stone is going up and down, and at this particular, this is at t equals 2 and this is at t equals 7. It's going down. This is positive and this one negative. Okay, let's go and do letter B. What is the stone maximum height and when does it reach that height? So maximum height, remember we talk about that when the slope, well, not this one, but when the when a particular slope here equals 0. Okay, let's go and solve it. When is the slope 0? When the derivative equals 0. And in this case, which is my derivative? My initial velocity, which is 50 minus 9.8 t, and that should be 0. If we solve for t, we will have that t equals 50 divided by 9.8, which is approximately 5.1. So right here at 5.1 is when the slope is 0, the maximum height. But which is that height? Well, we have the position equation here. So let's use it. S of 5.1 equals 10. My initial position, which is here, okay, plus my initial velocity 50 times the time 5.1 minus 1/2 gravity, which is 9.8 times the time squared. 5.1 squared, which equals all these, well, not equals, is approximately, that's the difference between an equal sign, 137.6 meters, and that is my answer. In this case, this one, and these ones are the answers. Understood? Okay, let's go. Well, in this case, we had an initial position and an initial velocity. Now, in the following example, we're gonna be, let me erase all these, if you wait a second, please. In the next example, we will have to find the initial conditions using the same equations. So, sorry, it's taking, but I didn't want to erase the formulas for you. Okay, so let's do now example number 7. In example number 7, what is the initial velocity? Initial velocity, that's what we want, required for a bullet fired vertically from ground level to reach a maximum height. So S of t of 2 kilometers. 2 kilometers. Okay, so we need the formula as a function of initial velocity. Remember that the velocity equals the initial velocity minus gravity times the time. Based on that, we can solve for the initial velocity. Okay, well, this has to be 0 at the beginning, because at the beginning the initial height, it's 0, S of 0. So using that one, the bullet's height and the velocity is 0, then we will have that the time t equals my initial velocity over my gravity. Okay, so that maximum height is the value of S of t at that particular time. Okay, so let's solve that one. S of the initial velocity over gravity, that's the moment that we are going to be using. Wait a second, please. This will be, if I use, remember the formula of the position, the same formula, it will be my initial velocity. Remember that the position is 0, it's starting from the ground. So my initial velocity times the time, which in this case it's the initial velocity over the gravity, minus 1/2 the gravity over the time squared. Initial velocity over gravity, all this squared, which will be initial velocity squared over gravity minus 1/2 of the yes, initial velocity squared over gravity. Yes, which will be, it's 1/2 the initial velocity squared over the gravity. Yes. Okay, now we can solve for the initial velocity using the value of gravity. Okay, so the maximum height will be the initial velocity squared over 2 times the gravity, which will be my initial velocity squared over 2 times 9.8, which equals approximately 2,000 meters. Okay, now that means that the initial velocity will be the square root of 2 times 9.8 times 2000. Why 2000? Because they told us that the position was 2 kilometers, but we are talking about meters, so that equals 2000 meters. Okay, and this will be approximately 198 meters per second. In reality, the initial velocity will have to be considerably greater than that because of the air resistance. But this is the solution and the answer for that example number 7. I hope you understood these problems. Just like going back into this one, they asked us to find the initial velocity for that bullet that was fired vertically to reach the maximum height of 2 kilometers. So we wanted to know when it reaches those 2 kilometers. Okay, that means when the derivative at the very top it's 0, and we're talking about the derivative, which is the velocity, because that's the change in position. That's why I equal that to 0. Okay, and based on that I found, like I solved for t, and I used that in the position, because at that time it's when the derivative equals 0. Now this is the time. I plug in that equation here, that value here, and I solve for the position. The position is this one, and they gave me when is that position, when s of t equals 2 kilometers. So I equal that b squared over 2 times g, gravity, 9, and it's 2000. Now I can solve for the b initial. Okay, understood? Well, I hope with these examples, which are a lot, you are able to solve the homework. Good luck.